Hello everyone. In this video, I'll talk about Maxwell's force equation, the Maxwell-Ampere law. So if you haven't watched my three videos that I'm talking about Maxwell's first, second, and third equations, I'll recommend you to do that because this equation is highly related to his other equations as well, the other videos. So let's go ahead and get started. I'll first explain it visually. So what does Maxwell try to convey us? And then I will go through the equation itself and then kind of relate this to. Let's go ahead and get started. All right, so imagine a simple long straight wire carrying a steady current, just like you see here in this video. So the current will be going from positive to the negative. This is how so this is kind of direction of current. It's just a simple wire. You connect it to the battery. Well, the electron's movement is actually from negative to positive, but it's accepted that the current was invented, discovered long before the electrons were discovered. So that's why we always assume that the current moves from positive to negative side. Okay, so what does Ampere's original law says us? Not the Maxwell-Ampere, but the Ampere law. So this current, it says that this current generates a magnetic field that circles the wire in concentric loop. So we have this kind of loop. So that's what we assume, that it's magnetic field that's shaping, that's forming around this wire. It's due to the electric field. So the strength of this magnetic field, so I'm just gonna write this magnetic field. So the strength of this magnetic field, how strong it is, at any point around the loop is directly proportional to the conduction current. So the blue arrows, those are, as I mentioned, they are current, also known as, we also call it a conduction current. We can also tell it as a I enclosed. Okay. So this is very important. So it's conduction current. The strength of this magnetic field is directly proportional to the conduction current, which makes absolutely sense, because higher the current, the stronger the magnetic field is, which shapes around the electric field. And by equation, it's written as this. So this is our magnetic field. EL is equal to this we call permeability, and then I'm just gonna write enclosed, and then we integrate it. So the integral means it's a closed. The circle in the within the integral, it means it's a closed loop, just like you see here in this diagram. It's closed, so there is no any open space between that. That's why we have this. So that works perfectly when the current is constant with no gaps or interruptions in the conductor. So Ampere's law describes how steady electric current generate magnetic field. In this integral form, it states that the line integral, so this is, you see the dl, that represents the, call it line integral. And you should already know the integral from your calculus class. So the dl, yeah, there is also dA, which is also mentioned, refers to this area. That's typically, we use dA as a for Maxwell's first and second equation, but dl is more like a line integral. So they generate magnetic field, and it in its integral form, it states that the line integral of the magnetic field, and again, this is magnetic field. This is magnetic field. So the magnetic field B around any closed loop is equal to the permeability of free space. What is permeability? This is permeability. Permeability. So it's permeability, so times the conduction current, and you already know that this term, the last I enclosed, it's a conduction current. So this means that if you imagine drawing closed paths, or we call Amperian loop, which is this is we also called Amperian loop. So the Amperian loop, it's encircling a current wire or current carrying wire. The sum of the magnetic fields is component along the path is directly proportional to the current flowing through the wire, as just I mentioned. And this works perfectly when in a steady current and a DC or direct current. Like this in straight line wires or solenoids, where the current is constant and there is no any change in electric fields. It works perfectly same. It makes perfectly sense. So the Ampere's law works well in this kind of situation, in this kind of the electric system or circuit. However, what if the current is not constant? What if we have some kind of dielectric material here? All right, so here I drew the capacitor here, right in the middle. So it has this dielectric material in the middle where the current doesn't pass. And as you see here, charges, the positive and negative charges here, they accumulate there. That's how capacitor works. It stores the energy, the electric field inside the dielectric. If you want to know more about this system, what capacitor is, dielectric is, so I'll highly recommend you to watch my previous video where I'm talking specifically about this kind of the system where the current is not stable. So, but if you have already watched it, if you'll know what exactly capacitors are, how the dielectric work, so just stay in this video. All right, so now this is the issue now. So the Ampere's original law fails in this situation where electric field change over time. So the electric field here is E field. We have is different than here. We have also E electric field. So these two are not same. These two are different. So now the current is not stable here. So in such circuit, conduction current flows in the wire up to the capacitor plates. Here is the capacitor plate. So this is the plate number 1, and this is the plate number 2. Plate 1, plate 2. So up to this point, up to this capacitor plate number 1, the current stays same. But then current doesn't cross the dielectric gap. Now we have this gap actually. Yet a magnetic field still forms around the circuit as the capacitor that charges. So we do have here magnetic field. So here we do have this B here. The B exists here, magnetic field. So how does it work? So we have magnetic field here, and we also have magnetic field here. So now there are two magnetic fields, but these two are different. So Maxwell realized that this apparent gap in current actually corresponds to the changing electric field between the plates. So this electric field here that I wrote, they are changing. They are not stable. This electric field, they are changing between the plates. He introduced the concept of displacement current. Now we do have a current here, but it's not a conduction current. We'll call it displacement current. And that proportional to the rate of change of electric flux to account for this. So now we have here a different magnetic field, as I just mentioned. Now we have a different electric field which is changing, so which means here we have a different current, which we call I displacement. So I'm just gonna erase some of these arrows. Don't want to confuse. So I just put those arrows when I was mentioning some terms. So I'm just gonna okay. So let's just clear things up a little bit. So yeah, so now just gonna rewrite this more properly. Okay. Now we have here I displacement. So displacement current. That's what Maxwell introduced it. So now it's the sum of both displacement and the conduction current. So now we can change the equation here. We can just gonna write a new equation. It's not quite new, but so it's a Maxwell-Ampere law. So now it's not quite new, so it's just a little bit modification to original law. So it's gonna be, so we're gonna write it as the integral, again the closed loop. So it's closed, even though we have a capacitor, it's still closed loop, there is no gap there. We still have a magnetic field vector, and there should be vector there too, times dl, again vector. And so now we still have a permeability, and it's the sum of conduction and the displacement current. So I enclosed plus I displacement. So it's the sum of conduction current and then displacement current. When there is no capacitor, the displacement current will be 0, and the law obeys this Ampere's original law. But now, if we have a conduction which have a capacitor, which means we have a displacement current, so now we do have to add this a new term, displacement current. So this displacement current is equal to, there's a specific equation for that, permittivity. What's permittivity? So when you have a dielectric material, you always have to have a permittivity. Excuse me, and permittivity. So that times a flux, the electric field flux. So again, if you have an electric field is changing there, that means the flux is changing inside the capacitor, inside the dielectric. So you have a flux, and how much it's changing now over the time. Now there is also time involved. So this is what the new term was added by Maxwell. So when we combine them, of course, we should get B times dl. I'm just rewriting everything. And then we have permeability times displacement current plus permittivity times electric flux. Okay, so this is the new modification on original law. So again, in such a circuit, and when there is just a current, when there is just a wire, the conduction current flows in a wire up to the capacitor plates, but no actual current closes when we have a dielectric gap. So we have a dielectric gap, the conduct doesn't close, but yet a magnetic field still forms around this circuit as the capacitor charges. So we do have a magnetic field here, as I mentioned it earlier. And then Maxwell introduced the concept of displacement current, and it's proportional to the rate of change of electric flux. So I'm just gonna, let me write this down, the electric flux. Sorry. So electric flux we have to account for this. So overall, Maxwell's law ensures that magnetic fields are produced not only by conduction current but also by changing electric field. So we do have a conduction current, and this conduction current does also produce the magnetic field. That's what we call from the Amperian. Oh, apologize. There should be a loop. So it should be Amperian loop. So the magnetic, but at the same time, also the magnetic field also will be created by the change of electric field. Not just the electric field, but the change of electric field within this capacitor, and making the law universally consistent and laying the foundation for understanding the electromagnetic waves.